them are to pair up and then come up with the right recipe on creating making a smoothie, right? So, all right, and we need to remove this line, okay? And I already did this in the other class, so I'm gonna talk about. Um, so I'm gonna kind of get it from that class. It's easier. All right. So I'm gonna just copy paste. Okay. Or maybe I can take this. Yeah. Okay. I need to this one. Sorry. It's really slow. All right. So this is my recipe. The recipe that I came up with. Okay. All right. So there may be like multitude of ways of making it smooth. Don't worry too much about having different ones, right? What important is numbering is important because this is the sequential steps that we gonna follow to get this done, right? So numbering is important because this is a sequential set of steps to get this thing done. And also, one other thing is in coding also, we will number code lines. So it's good to have that correspondence between here and then this English, right? In Python as well. All right. So, and also need to have at least one um, major step with sub steps. Like in here, for example, cut fruits and then the 2.1 is cut bananas, 2.2 cut bananas. All right. So um, the other thing is in your sub steps, use the numbering accordingly, like 2.1, 2.2. These are my recommendations, but there are many other ways. Like for example, you can go A, B, C, right, as well. And also, this indentation is also good because it's also kind of make it clear that this is actually right. So, and also in Python, we will use indentation because it's part of Python's grammar. Indentation is part of Python's grammar, part of speech. So it's good to have use that here in English as well. Okay. All right. Okay. So so basically um, so I'm gonna use the same and then go over here and then reply as a student. Okay. So if you miss this process and then this and like we will do this process repeatedly in this class. Okay. All right. Um, so reply. I'm gonna go here, so I need to save this. Okay, saved, and copy all the code, and then paste it, right? And make sure to change the formatting to pre-format. So this is code, still code, but it's with like code comments actually, right? Okay. And then in so you can use this button to toggle back and forth to HTML and text mode. So you toggle that and go to HTML mode, and then copy paste this template. Okay. So if you haven't still done this, guys, you can follow me and then do this. Okay. And and you can paste it over here. Okay. And then update this part right here with that link. Okay. So this link. Okay. Um, and that's it. Okay. So now you can always, before you reply, you can toggle. Okay. And then see if that worked. Okay. Looks like it's working, so I can now post. Okay. So and by the way, guys, do not attach images, right? So just we'll only see a file name, not show anything. Okay. So reply, and this is done. Okay. All right. And all. So let's say you made a mistake. You can edit by clicking on this three dots. Okay. And edit. Okay. So and then you can actually edit. Okay. Your posting. And also you, if you click on the discussion, these three dots. Okay. So you will see the rubric as well. So check out the rubric. It's a detailed rubric there, and then check it out as well. Okay. So TAs and I will use this rubric to grade you. Okay. And that's it. Okay. So that's the what we did on Thursday, last Thursday together. Any question before we start module two? So we are going to start module two today, guys. Okay. So one good thing I wanted to show you guys again in tutoring mode. Okay. I think it's better do it now because the attendance settled. All right. So to see your grades, you should click on that, right? And so I completed module one. So after module one, the submission should be graded. If you, unless you submitted like late last night things, right? All right, up to module one. Okay. So anything in module two haven't graded yet. So we'll probably be grading them towards the end of this week. Okay. So so this as a test student, I think I have okay this one. Okay. So you click grades and you can see your grades, right? So this is me as a test student. See that over here, you see this icon, right? So if you see something like that, right, then basically you can click on it, right, and then you will see the way we I use rubric, right? So let's say you didn't do it, then you will have like no marks, and you can read that, right? So please regularly check those. That's how you get our feedback. Okay, that's how you will get our feedback. Okay, and maybe I have more here. Let's see. See, right, and then yeah. No, I think that's yeah. So let me see. Yeah, so there's another rubric. Okay, so I think I have. Okay, it's fine. The other thing I want you guys to check is um, right. So for this one, you're gonna follow me now. Okay? Could you all click on this right here, inbox? Click on that, please. So I have one email, right? So that's where you're gonna get from when I send an email from Gradebook, you will receive it in your inbox. Okay, so please regularly check that. At least once a day should be fine. Okay, and then also if you click over here, so I'm gonna quickly show you. Okay, so click on your profile photo. Okay. So, all right. Um, So, um, all right, click on your profile photo and then click on notifications. Click on notifications. All right, click on notifications. And please, okay, so you decide. This is up to you, right? But turn on some of these notifications so that you will receive an email from Canvas. Say something is about you, and you get that email from Canvas. Okay. So that's important, okay, guys. And also, maybe see, I can, um, yeah, and then you can see that right here, email, and then if you have an app, Canvas app, you can also get push notification. Okay, so you can see that I turned on majority of notifications because I want to respond to you, right? So I get emails whenever you do submit something, those things. Okay. All right, and then there's and I think there's one more. Let's see, probably settings. Um, yeah, you can add your personal email here and then get notification to that one as well. Let's say you're not regularly checking your school email, you can add your personal email and then you can get those notifications to your personal email. Okay? So I highly recommend doing those. Okay. Again, because we have in order to communicate clearly and efficiently, right? So we have to check those, right? So that's why I'm showing you guys all this. Okay. All right. I think you're ready to move on. Okay. All right. So we're gonna start chapter 2. But before we start, any question? No. Chapter 1. And any other question? Any logistic issue? Anything? I know I fixed. There were a couple of broken links. I fixed them. Yeah, a lot of the links. I removed some pages, right? Yeah, I removed them. Yeah. Yeah. So I removed them. Yes. Um, what happened is when we import, so this class is a copy of previous class, right? So I copied that canvas to this one, but sometimes the link doesn't carry. So it still end up with the previous class link, so you can't open it. All right. Any other questions? All right. So let's move on, guys. Okay. All right. So again, this again import module, but some of the topics are conceptual. So just reading and understanding enough. So I'm gonna roughly go over them quickly. Okay. So all right. So let's talk about the basic component of computer. um, we know that CPU is the brain, right, of the computer, and it has two parts, arithmetic and logic units. We call it ALU. Basically, it performs simple addition, subtraction, those kind of simple mathematics, and also or those kind of logical operators. Okay. So the language is basically in binary format. Okay. And the control is basically controls the other components of the computer. Like controls the hard drive, controls the memory, those things. So two parts, ALU plus the control unit. Okay. So memory basically we call random access memory. Okay. What do you call random access?
I think I watched something on there as we were developing memory. They realized that like they could save time by just like any place that they are, they just randomly go to
Yeah,
the circuits.
you're right. So basically, if you know the address, you can directly go to that address. You don't have to go from top and then go to the table like thing and then go to that place, right? You can directly go to the memory that you want to access. So that's basically random access. Yeah. Yeah. And then so that's memory, and then we have input devices. So here is the keyboard. What are other input devices? Yes.
Like a touch screen on your phone.
Yeah, touch screen is one. Yeah. What else? Keyboards. We have other ones.
Like the USB port.
Yes. If you are reading through it something like you are reading a file through it, that's an input answer. So USB port is anyone? Mouse. Yeah. Mouse is a input. Anyone else? Microphone, yes, an input, right?
And the camera.
Camera also an input. And internet also an input if we are reading from internet, right? If we are sending into the internet, that's an output. Okay. So that brings us what are the outputs? Screen is the usual output, right? So, but you can also write into a file or disk, right? Hard disk. So that's an output, right? So reading from a file is an input. Like you double check the file in your computer, that's an input. But if you are creating a file inside, let's say you are creating a Word file, that's an output. Okay. Um, what are other output devices?
Screen.
Screen, yeah, you already got that one.
Printer.
Yeah.
Printer.
Printer, yes, yes, printer. And anyone else? Speaker, yes. Speaker is an output. Okay, device. All right. So go down. All right. Clock speeds. You may have seen these, right? The 1 gigahertz CPU, um, 4 gigahertz CPU, right? So basically, it's basically tells you the the how fast your CPU runs. Okay? So, and then there's an example over there, right? So, 1 gigahertz means your CPU execute 1 billion cycles per second. So, usually, if it is a simple instruction, let's say for you are adding two numbers, like 10 plus 20, right? So, the instruction is that sum operation, right? Right? Summing up operation. So, that's a simple instruction, right? Usually a CPU,
He's touching the fire.
um, um, so CPU in a single cycle, CPU execute a single cycle to execute such like simple addition or multiplication. Okay. So knowing that is important because some instructions are complex, right? So they have multiple other instructions, right? So so those things may need more cycles. Okay. So simple instructions CPU usually execute in a single cycle. So it's basically execute that, and then basically in the next by the time the next cycle, it's ready to execute the next instruction. All right. So so basically that's what it actually basically do, right? So there's a specific mechanism to fetch this instruction into the CPU, right? So so you get an instruction, goes into the CPU, get executed, and it's now waiting for the next instruction. All right. So let's take a look at. So there's two CPUs, one 2 GHz, and then the other one is 4 GHz. So double the speed, right? So let's quickly play this one. Okay. So all right, and then if you play the other one, you can see that it's actually done executing nearly half of the time that it took for the first CPU. Okay. But again, there are lot of other parameters that this process depend on, right? So, for example, if the instructions are read from directly from hard drive, and then it's really slow now. So it's not the CPU speed, right? Now it's actually depend on hard drive sync speed, right? Which is really slow. Okay. All right. Let's do. I think we can do this one. So let's do number 3, guys. Right. So such as okay, blank can decrease the amount of instructions that CPU can decreases, right? So yeah, as CPU clock speed increases, I CPU temperature. Yeah. So the middle one. Yeah.
Is that because it just makes the electricity flow down?
Yeah. So when you pick up, the resistance goes up, right? So and then that means the count is more, right? Goes down, and then those can affect. Um, all right. All right. So we saw this one in the module one as well, right? The switch idea of the switch, right? So on is one and then off is zero, right? So um, basically in the language the computer speaks, right? So this zero and one are the two characters, right? So that's the script basically, right? For English, how many do we have? English language, we have 20, 26, right? How's 27? I don't know. Yeah. So for the computer, machine language, we only have two characters. Well, you can go to two, that's like yeah, so 0 and 1, right? So those are the two basically like characters that computer speaks. Yeah.
I have a question now. So each digit is binary, right?
Yeah.
So does the switch need a 0 and a 1 to be a full switch, or is each digit its own switch?
Basically,
Trying to figure out
so
how
in the transistor, yeah, it's actually so there are two states. Each transistor has two states. One is one, the other one is zero. So
each
usually, yeah.
each switch has that 0 and 1, or
No, basically it depends. It's a voltage state, right? So physically, so 5 volts usually three to 5 volts is the one state, and then below three is the zero state. So between 0 volt and 5 volt, usually those are the 5 is 1. Usually you have a threshold, let's say 3 and above is 1, and then 2 and below is 0. So those are the two states you can
Okay.
go back and forth. So, all right. So we're gonna get more into more today itself actually on this topic, okay? And then we also group them. Like for example, over there when we group 8 together, we call them a byte. Okay. All right. So bit is just either 0 or 1. Just one of them is bit. Okay. And then 8 of them together called a byte. All right. So so to represent numbers, this is easily we can use. Okay. So pretty much we have to convert from decimal numbers to binary numbers. So it's straightforward as that, and it's also universal. But to represent like these characters, right? It's not that straightforward. Okay? So the reason is basically, well, we have to come up with the protocol, right? And then if you don't have one, then many people will use their own ways of doing it. Now it's actually really confusing, right? So that's when in 1963 the American standard, right, introduced ASCII, right, ASCII to represent those symbols in the computer, right? So you can see that 32 start from 32, but 0 to 32 basically unprintable characters, so you cannot actually put them here, right? So they are there as well. So and it end up at 126. Okay, so it's actually 127 of them. Okay, so and you can see it includes these like frequent characters that we use in English, right? So the alphabet is there both big and small, and then mathematic like digits are there as well, right? So right here, and also the symbols that you use, right? So there's a big problem over here. What is the problem in this standard? Yeah, it's only English, right? And then numbers and then some symbols. So it's not that inclusive, right? Because there are other characters in this world, right? Like, other languages, right? Other systems, right? So this this was not enough, and then they soon realized that, but it took until 1991 to come up with the standard that it was everyone, right? So um, we call it Unicode, right? And you can expand it, like you started off with the 8-bit Unicode, and then now we have 32-bit Unicode. Okay? So how many possibilities do we have? How many characters can we represent in Unicode system? It's not endless, yeah. It's, okay. Mhm.
So wait, so we have 100,000 in that code? Is that what you're saying?
It's 2 to the power 32, right? If you take 32 bit Unicode, right? So that's many possibilities. Okay. So that's a lot. So nowadays you can even represent hieroglyphs in Mayan symbol system as well as petroglyphs in Egypt. They all have you can represent in Unicode. Okay. So and then that if we need more characters, then we can actually expand it to the next level. For example, for 64 bit, we haven't have we still haven't gotten into it. Okay. All right. So, but we're gonna come back to this topic again in types module 7.
I
Okay.
have a question about
Yep.
that. So when you're standardizing it, are you standardizing the
it's basically um, the basically you assign unique link pattern. Let's say a character in Mandarin. You take that and then assign a unique link pattern universally. So that's that, right? And basically then when you have font system, basically that's what the font system does, right? So take the read the number and then basically assign particular um, tiny image for that as a font.
And so is that done like when they're building the microchip?
No, it's not when they build the microchip.
It's saved in memory as like it knows that that series of bits.
Pretty much the operating system does that when it's actually read the operating system, load the operating system to the memory.
So it's not building.
No. All right. So, all right. We're gonna come back to this topic, guys. Okay, later. So I'm gonna go to the next topic. All right. So there's a so we talk about this megabytes, kilobytes. So you have heard, right? Gigabytes, right? Or gigabit, right? So and then we also say like like in in metric system we say kilograms, right? Um, those words there are too, right? So we know that metric system have very round numbers, right? Kilo is what? 1,000, right? Likewise, right? So, so following the similar pattern, but we have a similar pattern in naming digital bits as well, but it's not exactly those round numbers. Like for example, this we say kilo, but it's not thousand. It's 1024 has to be power of two. So the closest power of two is to the 10. That actually gives you 1024, not just 1000. So, but we still say it's kilobit or kilobyte if it is in bytes. Okay. So likewise, for 1 megabytes, it's this many, not 100,000. So sorry, 1 million, not 1 million, right? 1,000, and then like giga, like this one. Okay. All right. So let's do this one, guys. Number 7. What's the answer for number 7? Yeah, 64. Okay. I big B or small b? Yeah, big B, right? Because it's actually bytes, right? So bytes means big B. If it is small bits, then small b. Okay, I B. So check. All right. Any questions before we go on the next section? We go up to 8 today, and I will finish the module Thursday. Okay? Yes.
Powers of two because it's fun.
Yes. And then we're gonna learn it later today. Yep. After the interval of time. We still have time. All right. Cache, memory, and drive. Okay. So another two parts, very important parts of the computer is drive and memory. Okay. You can think of both as storage, right? Storage devices, right? But one is actually there's a big difference between the two, right? What is the big difference between the two? Drive and the memory.
So memory is a lot bigger, slower processing things, drive. I think
say memory is a lot bigger and slower compared to.
Oh no, no, it's the other way
Oh,
around.
okay.
Yeah,
Okay.
hard drive is a lot
Yeah.
slower than memory.
Yeah.
It's like 3,000 times slower.
Yeah. And so another big difference, function wise, is yes. And memory goes away when you sign off, right? And later on, you'll see that for that reason we call memory for for her reason we put there's a name for the memory. Call it unknown. That's down below actually. We call memory volatile because it goes away when we turn off the computer, right? So volatile goes away. And then hard drive, the information we store in the hard drive is not volatile because it stays there even when we turn off the computer. Okay. So that's actually the big difference. Okay. So, but two key things to remember is seeking from hard drive. We call the reading the hard drive for seek. Seeking from hard drive is really slow compared to reading the memory. Okay. So if and you may have experienced this when you actually use the computer, when you are especially in Windows, maybe old operating systems do that. When you are becoming close to use up all the memory that you are using in the computer, and it's now start switching to the hard drive. So we call it swapping, right? So when the computer starts to um, swapping, it becomes really slow, and you may have experienced sometimes get like freeze and basically end up rebooting the computer because reading from the hard drive is really slow because now the computer operating system use the part of the hard drive as the memory. So now it's reading from there, not from direct memory. So it's really slow and the computer become really stagnant. So we call it swapping. Okay? Swapping. And it's actually a really slow process. Okay? So same for even slower for the CD and the Blu-ray, all those discs, even slow. Okay? So reading from there. So let's quickly play. No, not this one. Let's go down. Okay. Maybe let's do this one together, guys. You guys gonna tell me first one. Prepare to run a word processor program. So basically, what you need to do is match the CPU actions. Um, run the program memory. No. Now we have to copy it from the drive, right? First one. Yeah. Because when we double click the word icon, so it's not in memory, right? Right? When you don't have any open word program open yet, it's in hard drive, the application. First need to start the application by reading it from the hard drive. So that's yeah. So this basically it goes to go after you double click and then once you load, now it's in the memory. Okay. So begin running the word processor program. Run this. Yeah, that's in memory. Okay. The program needs a document named resume.doc. Prepare to access that document. Where it's coming from? Yeah. Let's see. No, this one, right? Yeah. Okay. So basically, you are loading it to the memory. Double click on the file. It now goes into the memory. So this is a seek process from hard drive. Okay. The program access resume doc. That's in memory, right? So I think this is the one. Oh no, I think this is goes to this one. Yeah. So this one is there. Yep. Okay. All right. So let's play this animation. It's a good one. We compare two computers, same CPU and this one has, let's say, 2 gigabytes. This one has 4 gigabytes memory. So double the memory. Okay, and you can say that let's play. Okay, so the amount that fetch from the drive to small memory is small, right? So you have a small amount of information at the time when you run that program in the first CPU, okay, in the memory, right? So basically, you need to repeatedly speak from hard drive to read into the memory because the memory is small. Okay? So in the second one, you'll see that you can read bigger chunks of information from the hard drive into the memory, and it's now faster because you don't have to do repeatedly. And you can see the same program, right? Program one, right? So this is fast. So in general, the higher the memories, the faster the computer. All right. So like I said earlier, hard drive, and also including the solid state, it's a little bit faster than space hard drive. Um, and also then we have compact disc, like Blu-ray, DVD, CD. All right, cache is um, it's a memory, special kind of memory that's located inside the CPU. Okay, so basically, what we use the cache for is basically um, right. Let's say a program is repeatedly using piece of memory or piece of information, and then you don't have to repeatedly fetch it from memory. You can keep it close to the CPU. Okay? So that way, CPU don't have to request it from far because memory is outside the CPU, right? But cache is inside the CPU, so it's faster to fetch it, and also it's special kind of uh, memory that is faster, uh, running faster as well. So it's actually uh, small, but it's actually within the CPU, so it can actually fetch it really fast compared to directly fetching. Yes. So that would mean install libraries. Mhm. Is that part of the cache? It depends. Um, so basically, operating system figure this out, like what to put in cache, right? So usually, if we are repeatedly using this piece of information, um, when we do something, let's say process something, and then that something, if it fits into the cache, we can put it there in the cache so that we can easily, quickly access that and save time. Because fetching from memory also takes time, but it's longer than directly fetching from cache. So it depends on the operating system. Okay? So, and sometimes we generally use caching as well, like we cache it for like um, for efficient processing, right? So and it depends on the application also we run. Like sometimes browser cache information, um, so that it's a repeatedly used information, right? So and you can also there are advanced programming techniques to program the cache as well. All right. And you can see that right here, if you play this one, okay, and and then basically once we so put them in the cache, right, and then you can use it, um, right, so later on in the inside the processor. Okay. So the relative speeds, you can take a look over here, and you can see that um, the cache is the fastest, right? And then, but most why it's actually the memory is really small for the cache because processor is small, right? So you don't have a lot of real estate inside the processor to put more memory in there, right? So that's one issue. So it's usually megabyte to kilobyte. You may have seen this when you buy computers, right? Level 1 cache, level 2 cache, level 3 cache, right? L1, L2, L3. Those are actually talking about the caches. And then memory is nowadays gigabyte scale, right? Like 16 gigabyte computer. And then hard drive is nowadays in the terabyte scale. Okay. Usual, the typical values. Okay. But you can see that it runs really slower than the memory. And then we already talked about non-volatile and volatile memory. Um, so um, USB and then also like the solid state drive, the display hard drive, CD, they're all non-volatile memory. And then memory is volatile. All right. Let's take our break, guys. Almost 12. So be here around 12:06, and we're gonna watch a video.
Professor, I have a question.
Yeah. Yeah.
So, does the computer actually access information from the drive, or is it constantly putting it onto memory?
Well, when we turn on the computer, right, everything, um, we the the boot process loads on the drive into the memory, right? So operating system stays there usually on the memory for as long as we keep the computer on.
I mean, like in the situation of swapping, is swapping still happen on computers?
Oh yeah, yeah. I think it's still there. Yeah.
And so when it's,
Bridget, do you know like, more information on swapping? It's yeah, I know that when you like when you partition for Linux, especially I know that it actually asks a separate space for the hard disk for swapping, so it keeps it separately. But Windows, it's always is determined where to put at the moment swapping needed for Windows.
because like, so when it's swapping, is it deleting stuff from memory, putting new stuff in so that it can track?
No, because memory is now full. So operating system decides some yeah, some information. Then they say we want to open a new file, but the memory is full. The new file may want to again the hard disk.
So it's not constantly deleting memory.
No, no. So it may even begin like not. It may not wait until it's full. It may start stopping when it's becoming close to full. The memory. Yeah. So that's when you realize it's really becomes it's really hardly stopping, and you will see that computer is really slow because switching is really slow. So usually it's um, I think there's a cap for the stopping as well, less than the usual memory. Bridget, it was him I was talking about. Getting help after the you have this one, correct? All right, so let's watch, guys. So I just published it, guys. Could you all refresh the module? Please? It's in module two. Okay. So this the content kind of the video like the content the the examples he takes is not that relevant, but the idea is really important. Okay? So basically, it talks about the end goal of learning, right? So what's the end goal of learning? We should be able to create something from the thing that we learn, right? So in this class, you guys should be able to create a simple Python program to solve a problem. That's the goal of this class in the end, right? So we should be able to create something from the thing that we learn, right? So this guy called Bloom, actually in the 50s, maybe 60s, came up with this pattern on the objective of the learning, and then it was revised in the 90s actually. Okay, so let's watch.
According to Bloom's revised taxonomy of cognition, there are several levels of thinking, ranging from the simplest forms, such as remembering and understanding, to the highest levels of thinking, such as creating something new from what you have learned. Professors ultimately want you to get to the highest levels of thinking, but notice, the highest levels of thinking rest on the foundation of the lowest forms of cognition. In other words, your ability to think critically will depend in part on what you remember and understand. So, the first step in becoming a great thinker is to spend time memorizing and understanding information. The more you know and understand, the better your critical thinking skills may become. After memorizing and understanding information, you also need to practice engaging in higher forms of thinking. How do you do this? A particularly effective way is to anticipate and create the questions you think your professor may ask on exams, taking care to make sure your questions reflect the different levels of Bloom's revised taxonomy. For example, remembering questions are those that involve recognizing or recalling facts, such as, in general, what do vampires look like? Or, what time of the month do men turn into werewolves? Understanding questions are those which involve explaining or describing concepts, such as, describe the steps involved with changing from a human into a vampire, or, why is a vampire a threat to society? Applying questions are those which involve taking what you have learned and connecting it with real-world examples, such as, knowing what you know about vampires, which one of your friends is most likely to be one? Or, considering your own health, are you a vampire? Analyzing questions are those which involve examining the components of a concept, especially to compare the concept with another concept. For example, compare and contrast vampires and werewolves. Evaluating questions are those that make some sort of a judgment supported by evidence, such as, which is better, a vampire or werewolf, and why? Which, a vampire or werewolf, would be most likely to win the Ninja Warrior competition, and why? Creating questions are those that involve taking what you know and generating something new with it, such as, what type of creature would you have to be in order to fight both a vampire and a werewolf? If you were allowed only one tool, what tool would you create to defend yourself from both vampires and werewolves? Generating critical thinking questions can be a challenge, but with practice, you can effectively anticipate your professor's exam questions. If you have
All right, guys. So that's about that. So let's go back to our um, this one right here. All right. Talked about types of computers, right? So when we have the internet pages, there are servers, right? And PC is all in front of one, right? So then we have smartphones and then tablets. So these are like kind of visible computers, right? And then we have embedded ones as well. Okay. I think that's about that this section. Yeah. All right. Moore's law. Basically, it's the relationship between um, the size of the chip and then the time frame, right? So so there's a I think this guy is from Intel, right? He came up with this pattern. Right? So and if you can see that over here, right? So this is the um, number of transistors per IC, right? Or the chip or a chip, right? And you can see that around like it started like exploding around 2005 and then onward, right? So and you can see that this it's a log like exponential curve, right? So basically the trend is what's the trend here? Yeah, but one specific trend. So uh, yes. or this one is log, right? You scale that, so this exponential, so like in go to the n kind of, right? And then if you take the log base 2, right, it become a line graph. So this is actually a log base 2. Okay. So basically it tells that it's actually, I think every year or every 10 years it doubled. Take a look. Um, yeah. So it's actually every year doubled, right? You can actually take a look from here as well. Um, but there's a limit, right? So uh, you cannot forever go and then scale small, right? We already I think talked about this in last week too, right? So we have what should be the end, right? And it's close to little bit larger than silicon atom, which is 2 nanometers. Okay. So because even you take a single silicon atom, it uses its semiconducting properties. If you take one single silicon atom, it took I think at least single silicon crystal, which is about 6 atoms together in a single most tiniest repeated pattern that we have in those wafers. Right? So we call it a single crystal. So usually I think 6 atoms together. Once we go beyond that, silicon uses its semiconducting properties. So that's the scale.
Are we anywhere close to that?
We are already at that. So the way we now increase the chip, density is we vertically grow now. So earlier we grow flat, right? So the chip is in two-dimensional scale and it grows this way. So the more transistor you have, the more it become larger, like area-wise. So now you keep the area constant and you can go a little bit several layers by layer vertically as well. So that's now vertical growing chips as well. And then you can also um, use parallel technique like parallelization technique as well. Okay. All right. All right. So clock frequency also increase with time. Okay. And you can see that it's actually now kind of plateauing now. So that means the you can also make forever faster, right? So there's a limit there as well. And then next frontier probably will be quantum computing, much faster speeds, right? But we kind of we still not there yet, right? So there's a lot of research going on for that, but still um, general people cannot use quantum computers still. Okay. The challenges there is basically again the smaller you get, the larger the leaking current. So it really become heat. So heating is a really big issue when your chip become really smaller and smaller, and that heat generated could be easily damaging. So you need to have special cooling system, like system to cool down that heat. So it's actually takes a lot of power as well because leaking current means you um, waste a lot of power as well. Right? So that's actually one of the reason. Like yes, the CPU speed got enough. At the same time, computer now uses a lot of power as well. All right. And then there are embedded computers, and then you can see that. Um, Even like the tiny headphone also has a controller chip, right? That you can call as an embedded computer, embedded chip. Okay. All right, hardware things, and then cloud storage industry is booming, and at the same time AI is booming, right? So all of those uh, data need to be somewhere, right? And we call them data centers, and those big companies, those that are like smaller scale companies as well, um, need to have storage facilities and computing storage both, right? And then they consume, you know, megawatts, or maybe even megawatts of power. Maybe 1 megawatt usually can power small village, right? And you can see that one data center use several megawatts of power. So if you directly connect it to the local grid, now it's draws down, even they even crash the grid as well. So they have their own power. So they usually go to the places where they can find cheap power, like close to a hydropower plant, or they can directly get a wire from the plant or nuclear power, right? Or sometimes they may even move to a state where they have cheap power, like for example Texas. A lot of tech companies move to states like that so that they can buy power cheaply, right? Because Texas laws are not as strict as here, right? So they have coal power plants, so they can get cheap power from coal. Yep.
So what they have here in the Silicon Valley are data centers. That's
Yeah, so we have some data centers here, but usually they are located in rural areas. So there's no competition for power, so they are pretty much safe because grid is not that consuming local power. So those areas, yeah. So not like big metropolitan areas. No. So pretty much what they do is like management is doing from here, but the actual implementation is somewhere in remote places.
I have a question. I
Yep.
don't know if you can answer it, but I'm really curious. So, what is the like? What do you think the standard practice is? Do you think they try to spot rural areas close to power centers, or have they ever built data centers where there's cheap land, right, rural areas, and then they will, alongside building that, will build power source? Is
Um,
that like common? Has that been heard of?
I think what they actually cherry pick places where the power is cheap and then go to those places. Yeah. So it's usually that trend that I have seen, like Utah has data centers, and also location also something important, right? So like if you are in the middle of the country, and then the access is kind of spread out from there, right? So and also maybe the internet bandwidth also a factor, right? So that also there. Sometimes they kind of like I have seen Amazon, those big companies, they themselves build the network infrastructure so that they can move there and use it.
When you say network infrastructure, what do you mean?
Like like internet
Oh,
cables and those you need a lot of bandwidth, right?
yeah.
It's a data center. So yeah. Um, so I have seen some cities protesting against coming those data centers. Those things are there because they can draw a lot of power and then they when the local community need a lot of power, speculate things happen, right? Those things are there as well.
What companies build a data center in some places to drive up the power of the cost of energy?
It depends if they have their own power, it will not. But if the demand goes up and then the power company
Charge more.
yeah,
So
more
that
than
they
so
go.
yeah, that depends again. So this is a good discussion. Yeah. So
Well, the reason I asked is because
mhm.
power than they were in community. So
Uh,
I thought it was interesting this idea that a company, like a corporation, a multi-million-dollar corporation, could drive like rural development by deliberately choosing rural areas to build data centers
yeah,
and then building the electric
yeah,
infrastructure to support it,
like surrounding infrastructure,
thereby
right?
also
Yeah, yeah,
providing.
that's actually true. Yeah. But I'm not sure the motive is there, but sometimes like some companies they have good motives, and they want to help other areas also part of the development along with that. Um, but I'm not sure the facilities located at Fremont. I don't know whether I don't think Elon Musk developed infrastructure at Fremont.
Not all the rural places.
Yeah, it's not wrong.
That's
Yeah,
like
you're right.
multi-million-dollar real estate.
Yeah. So, but yeah, you're right. Like, if they definitely contribute with the job market, right? So local job markets. And, um, sometimes they do, like, for example, like, data center company may choose to locate to, like, let's say, Mahavi Desert so that they can buy cheap wind power. That's a good motive, right? So, and then use that, right? So, and then
Use the solar energy.
yeah, solar, like you develop their own solar surrounding. Yeah, those are good motives. Some do like that, but usually depend on money. They want to save money, they'll go for that um, compared to other options, right?
When I was in high school, when I first learned about that, I thought build that in naturally cold areas because I think it's more resource conservative,
Mhm.
more resource intensive to cool than it is to heat.
Yeah, yeah, I think you're right. That's a good point. Yeah, so like surrounding environment is also cool, right? So you don't have to use a lot of over your own cooling system. So that's also a good point. Yeah. So maybe they start building maybe in Arctic, Antarctica. I don't know. But
Siberia,
yeah, maybe I don't know. But again, like you have to have other infrastructure, right? Yeah, Yukon is cool. Yes, and then probably close to good grid as well, right? Um, all right. So and then self-driving cars. A lot of conceptual topic, guys. So please read through them. Okay, so I'm gonna go into this one. This is really important. So this is the one that I skipped. Remember, I skipped a section that includes this one. Okay, now I am going to. Okay, so how do I do this? I don't want to spoil this to you guys, so I'm gonna for a moment I'm gonna disconnect because I need to close this and then I restart. So I need to dump this. All right. Okay. So uh, all right. So imagine I'm gonna take a different number, right? So I'm gonna take um, let's say it's a good number. Uh, let's take a 3D number. Let's say 567. Okay, five. Six. I'm gonna put some spaces. Seven. Okay. All right. Here's my question. So take three combination of integers that sum up to this number. Okay. Imagine, like I would say 400 plus 100 plus 67. Right. Would add up to 567. Right. Okay. So one question is, so imagine three numbers that could sum up to that would sum up to this number. Okay. Three integers. First question is, at ballpark level, how many such unique combinations? I mean, you don't have to be a certain value, like just throw numbers. Yeah, so add up to this one, yeah. So, but three numbers you are adding, and then that would give this one. So, I mean, we can think of it's a huge number, right? Huge amount, right? 567 to the power of 3. I can do 64 plus 2 plus 3. Yeah, so that's, I mean, you don't need to give me a specific number, but you can throw like, like generally how much would be like that. That's a lot, right? That's a lot. It probably could be in trillions. Combination. And you don't have to be certain. Probably there's a way to mathematically find this. We don't need to go there. But I would say yes, trillions of such combinations exist. Okay. Like, imagine like you can write 100 plus 5 plus then the rest 500 plus 1 plus 166, right? So there are so many combinations. So if you add up those combinations, you count all those combinations, probably in trillions, maybe even more. Okay? But among all of those combinations, there's a one combination standout. My question is, what is that? It's the closest power to would be the first number. No. Think about it. There is so okay. So let's say that there are trillions of combination of three numbers adding up to 567, right? Among all those trillions, there's a one combination really unique and stand out. What is that? Yes, that's it. Okay. 500 plus 60 plus 7. So let's write them. So I'm going to first write few examples. 400 plus, let's say, let's say 150. So this one just a regular combination. So what's the rest? And 17, right? So this one. So I'm gonna go for the one that just got you guys gave me, right? So 500 plus 60 plus 7. So my next question is, why this is unique? Okay, so very close. Hang on here. Very close. Yeah. Almost the answer. Are you little bit more specific? Yeah, so basically, so we call it like this is like um this is this, right? So if we go right, so we call this is the what place? 100 place, 10 place, 60 is 10 in 10 place, and then the ones place, right? So those are that's why, right? So let's make it more clear now. So I'm gonna write this 5 times 10 to the 5. So 10 to the 2. Oh, well, I'm gonna write it like this, and I'm gonna come back to very specific again. So 6 times what? 10, and then 1 times. Sorry, 7 times 1. So right. So we're gonna go even finer, right? So and now we're gonna see the actual reason. 10 to the power 2 plus 6 times 10 to the power 1 is 10, right? So and 7 is what? 7 times 10 to the power 0. This one 0. 1 is any number 0 power is 1, right? So now you see the pattern, right? So now it makes sense what we say. That is the one position, the middle one is the 10th position, and then the leftmost one is the 100th position. Right? And if we have one more digit to the left, then that's actually thousands. Likewise, we go increase. And if you go beyond the one position, now we are in the decimal level. So 10 to the negative 1, 10 to the negative 2, likewise. So we're not going to deal with those in this class, so we're not forget about having decimal points. Okay. All right. Now among these three, so this is the most unique and then most special combination, which we call these digits, right? We call these digits. Okay. And oh, this is the decimal number. So what is the base? 10, right? That's why we have this. See that? The base is 10. These things are in tens. Okay. So which digit carries the highest significance out of the three? 5, 6, 7 are the digits. Which one carries the highest significance? Yeah. Yeah, the 5 is the most significant digit. Why? Because 5 represents 500 of all the sum, right? So see that 500 is represented by 5 there, right? So all is the most significant digit is the leftmost one. The least significant digit is the rightmost one. Okay? In between we have other values. Okay? So, it's good to know this stuff and other patterns that you guys need to recognize is that the base is 10 decimal base 10 and the breakdown is based on 10 to the powers, right? So if the base is 8, then what should be the breakdown in what powers? 8, right? 8 to the powers. So if the base is 2, then what must be the breakdown of the powers? 2, right? So basically, for decimal number, the breakdown is like this. And then basically when we go to another base, let's say base 2, which is the one, the language that the computer speaks, the 0 and 1, right? The binary base. And actually the power of 2, right? So what else? So basically, the other thing to recognize is in base 10, how many unique digits do we have? 10, right? What are the 10? 0 to 9, right? So those are the unique symbols. The single one we call a digit, and we have 9 unique symbols to represent base 10 numbers. Okay. So for base 2, okay, so before we go to base 2, so base is 10. What is the last digit? 9. So remember, pattern is 1 less than the base is the last digit of the number system. Right? So if the number system is decimal, base is 10, last symbol is 9, 1 less than 10. So if the number system is true, binary, then what is the last symbol in the digits? 1. So the number of digits we have in the binary system is 0 and 1. That's it. So as simple as that. And now can you imagine like in zeros, 1, all of these things are we dealing with stored in the computer and we are dealing with all the internet, all the zeros and 1, right? It's all about how to arrange them. Okay? I'm gonna learn some of this that in this class. Okay? All right. Any questions? So you learn about the base 10 number system. By the way, guys, how that originated? Like in human history, like probably 100,000 years ago. Yeah, because we have 10 fingers, right? So they didn't have a specific name, but they may have used like 2 fingers to represent two killed animals, right? Two killed impalas, and and then basically as the civilization grew, like in Middle East, the 1 to 9 originated. I think in the Mohenjo-daro Harappa, they had the 0, right? So we call it Indo-Arabic number system. Okay? So the real symbols, but the actual numbers even originated before, like using the hand, other like maybe number of stones they may have used. Okay, so All right, so we're gonna go up to the next module. I think so. That's we're gonna start our lesson. I think we can now stop and do our group activity today. So you can see that. So here's a binary number, right? So this one has 4 bits. So the base is 2, and when we use the same pattern to break it down, so now the base is 2, so we're gonna use powers of 2, right? Right? So starting from 2 to the 0 to represent one's place, and then to represent two's place, not ten's place, right? Because we are in binary now. 2 to the 1, 2 to the 2, right? And we adapt it, and then you can use that. You can see that that's actually 13 in decimal, and we have written it in binary. Okay? So Thursday, guys, really important class. Please do not skip because we're gonna learn about how to convert between number system back and forth. That includes binary, octal, hexadecimal, and decimal, so between. Okay. Any questions? We're gonna stop right here now and come back to this and finish this module on Thursday. Yes. On the recommended video, do you have a video on how to convert between binary and decimal and decimal binary? You don't have a video on hexadecimal or octal. I can recommend one, yeah. But we will do it in the class, hands-on. Yeah. But yes, I have my own. If you work already. Yes, right here. I think I have shown it in here. Let's see. Um, this is the one. You guys, I need to read this or some windows. Sorry, videos are here. Oh no, I think not this one. Probably some of these videos cover that topic. Um, this is, oh no, this is the wrong module. Sorry. Um, yeah, module 2, right? Yeah, there you go, right here. This one. Um, I think yeah, some of these. Yeah, conversion between this is probably one of these. Okay. Take a look, yeah, but I can provide more as well. Yeah, I think the next chapter, starting from chapter 4, we have my own videos. Yeah. Oh yeah, see this one, how to convert decimal to binary, binary to decimal. Yeah, there are some. Oh, yeah, I can. Yes, yes, yes. But we'll do hands-on on Thursday on that. Yeah, I'll show you guys. But yes, I can actually look for more videos of that. Yeah. All right. All right. So we're gonna switch gears, and then I'm gonna just turn on this one, guys. All right, this one. Oh, I think me. Did I? Yeah. There you go. It's published in module 2, guys. Abstraction in real world is the topic. Okay. I'm gonna give you a quick summary. Right. So we talk about a little bit on abstraction. Okay. But think of basically, you know, having a lot of information to digest it's a problem, right? I mean, we don't like it, right? And that's include like doing to do something like having to read pages. It's kind of you know um, um, frustrating sometimes, right? So the general human tendency, right? So and that's why we have like words, verbs, and words in English, right? So that it has a meaning. So we don't need to uh, uh, like digest all the information that defines that word, right? example, right? I by the look of it, I know this is the chair, right? So I don't have to describe it to someone else, like saying the telling the features of it. I can say just grab the chair, right? So the person knows by looking at it, it's the chair, right? So we don't have to worry about how the chair works, right? Those don't need to be we don't need to bother about those, right? So that's abstraction, right? So um, like thinking about what it does rather than how it does is really important. It's important in day-to-day life, in English, as well as in computer science. So we're gonna learn that in particular to programming in week 5 when we learn function. But for now, we're gonna stick with English. So abstraction in English. So basically, any day-to-day thing that we do is a process, something that we do, right? So that means we use a verb in English, right? So we use a verb to represent an action or a function in English, right? So that's why I say in my example, right, make bread, right? So that's my example right here, make bread. Okay. So what's the output? The bread, right? So we worry about the output. So as long as the bread machine gives me a bread, I'm usually okay, right? If it is giving me something else, right, then I'm worrying now, right? So, but I need to know how the ingredients I want, the input, right? So this basic process, input, there's a process. Process is we don't need to pay too much attention to the process, right? But the most important thing is the output, the bread. Okay? So closing the process inside the box, let's say the bread machine, right? Only understanding the bread machine from its outside and then interacting with it's called the abstract, right? So you don't need to worry about too much what's happening and how the bread making process happens. Like how is the coil of the heating coil? You don't need to worry about that detail, right? So if we need to have the recipe and then the inputs and put them together and then make the bread, right? So that's abstraction. So what you guys need to do is come up with the simple process like this. So let's first take a read and then pair up, come up with the simple process. Like one word and one name behind, like make bread, write email, anything, right? So make sure you bring the verb to the front. So we are dealing with simple present tense in active voice. Verb comes first and then the decorating item after the verb. So yeah, so that's what we are going to do. And then you're going to draw a diagram like this. You can use technology.